Le Chatelier's principle is a chemical equilibrium principle that focuses on the balance between products and reactants. Le Chatelier's principle indicates that you can push a reaction towards one side versus the other. In an example of having blue copper sulfate solution, by reacting it with potassium iodide, it forms a brown, opaque solution. This then can be pushed to a different reaction by adding ammonia. The reaction itself, the solution, becomes a dark blue color. By neutralizing the ammonia, by adding hydrochloric acid, the reaction can then go back to that original brown, opaque solution. Overall, the reaction is driven from one side to the other depending on the chemicals involved, pushing it either one direction or the other. This is based on the fact that these products and reactants are either being added or removed from the initial reaction of copper sulfate and potassium iodide. Le Chatelier's principle is a chemical concept that deals with maintaining the balance or equilibrium of a chemical reaction. In this experiment, we're looking at a number of different reactions and seeing how Le Chatelier's principle plays a role in them by causing some external stresses, changing the conditions of the reaction, and seeing what the results will be. Every reaction starts with the reactants, or the starting material. These undergo a chemical reaction and rearrange to form the products. Typically, this is straightforward, but many times these reactions occur in an equilibrium. There's a balance that needs to be maintained between the products and the reactants. What this means is that even though the reaction occurs and generates the product, there would still be some amount of reactant left over. In typical chemical reactions, you're looking at the reactants turning into products. This occurs with a large chemical ratio that favors the products. The bulk of the reactants turn into products. Only a tiny amount of the product would ever go back to turn into the reactants, but that does occur because that balance, that ratio between the products and the reactants must be maintained. Le Chatelier's principle is a way to control that balance, or at least a way to investigate it. And a chemical reaction can only do two things. It can either react to make more products, or it can react in reverse to make more of the reactants. That's all a chemical reaction can do. And there are ways to favor one side or the other. Typically, things that will generate more product is obviously if you add more reactant. If there's more starting material, you will make more of the more of the product. But also, if you continually remove the product, let's say in the case of a reaction that produces a solid, ions dissolve in solution, they come together and form a solid product. But those ions are in equilibrium with each other. as more and more of the solid product is removed from the solution, that balance is no longer maintained. And the only thing the chemical reaction can do is make more products. So it continually drives the reaction towards the products. There are also ways that you can drive the reaction in reverse back towards the reactants. If the reaction is in an equilibrium state, if you're able to remove some of those products out of the test tube, out of the beaker, now the reaction is no longer balanced. And to maintain that balance, some of the products will reverse and turn into the reactants to make sure that balance, that ratio between products and reactants is maintained. You could also add more products. So if you already have some of the products sitting around, you can add more of it to the beaker, and that will, again, upset the ratio between the two, and the reaction needs to correct itself. A visual example of Le Chatelier's principle can be seen with these two glass tubes filled with a blue dye. These two tubes are connected, and at the moment they are perfectly balanced. However, when additional dye would be added to one side, these tubes are no longer balanced. However, in a reaction, the same thing occurs. If you add either a product or reactant to the reaction container, it is no longer in balance. If the reaction was allowed to occur, the two systems, products and reactants, would go back to being balanced with one another. Whichever side you added additional amount to would overall go down, and the other side would increase. The same can be true if you're removing a product or reactant. By removing some amount on one side, again, the system is no longer balanced. But if a reaction is allowed to occur, the side that you removed some of the sample from begins to increase while the other side simultaneously decreases. Overall, at the end of the reaction, both sides would be balanced, again, not necessarily equally, but they would maintain a balance or an equilibrium between each other. There are 6 chemical equilibrium reactions that are being investigated in this experiment. The first reaction is the equilibrium between chromate and dichromate ions. Solutions of chromate or potassium chromate are yellow, while potassium dichromate is orange. The chromate itself undergoes an oxidation reduction reaction to form dichromate. This reaction occurs by reacting with acid, in this case, reacting with sulfuric acid. You can watch the reaction occur going from yellow reactant into orange product. The second step in this is adding sodium hydroxide. Sodium hydroxide does not occur in this reaction, but it does affect the reaction. There are only so many molecules contained in the beaker or in the flask. And when one ion or one molecule can react in multiple different ways, these are competing reactions. In this case, the acid molecule or the acid ion H+ can react with the chromate ions to form dichromate ions, or it can react with hydroxide to form water. In this way, it is removing some of the H+, and that is turning into water. Therefore, in relation to the chromate-dichromate equilibrium, the total concentration of H+ was removed. A reactant was removed from the equilibrium equation. And what that does is shift the reaction back towards the products, or I'm sorry, back towards the reactants to maintain that equilibrium. And you can see that by when you're adding sodium hydroxide, the dichromate solution, which is orange, goes back into the yellow chromate solution. The second reaction is also a chemical reaction involving potassium chromate. However, this time it is a precipitation reaction with barium chloride. The potassium ions and chloride ions are spectators, while the barium precipitates with the chromate ion, producing a pale yellow solid of barium chromate. The next step is adding acid. When the acid is added, the solid dissolves and it forms into a clear orange solution. There was a side reaction that was happening, a competing reaction that occurred that made the solid disappear and turned the entire solution orange. The third reaction looks directly at concentration and solubility of solutions. In this reaction, saturated sodium chloride is at a concentration of 5.4 molar. This is the saturated solution where any additional sodium chloride would not dissolve. The water in this solution is completely saturated with sodium and chloride ions. It cannot contain any more of these ions. In this reaction, there are two steps. The first reaction is adding 12 molar hydrochloric acid. In this step, you see a precipitate form. You're starting off with saturated 5.4 molar solution, and you're adding a concentration of 12 molar chloride ions. Overall, the concentration of chloride would be between 12 and 5.4 molar. However, since 5.4 molar is the cutoff, you see a precipitation in this. By adding additional chloride, you're forcing the reaction towards the product of the solid. Likewise, by adding 3 molar hydrochloric acid, nothing happens. It stays a clear and colorless solution. While you're still performing the same actual task of combining aqueous sodium chloride and aqueous hydrochloric acid, the concentration plays a key role in this balance. By adding a low concentration of hydrochloric acid, the overall chloride concentration would now be between 5.4 and 3. The chloride concentration was lowered, thereby removing some of the chloride from the system and actually shifting it towards the ions themselves. At this point, you can add more solid sodium chloride and it would dissolve back into its ions because it is no longer a concentration of 5.4. It's between 5.4 and 3. The fourth reaction looks at the precipitation of iron 3 hydroxide. Iron 3 nitrate is reacted with sodium hydroxide to form a brown solid and soluble spectators sodium nitrate. There are a few different steps in this reaction. After the brown iron hydroxide is formed, hydrochloric acid is added. Acid, again, can react with hydroxide, thereby removing it from the system. Some of that hydroxide is leaving this iron solid, it's leaving this equilibrium reaction and forming water with the H+. You'll notice this becomes a bright, vibrant yellow and clear yellow solution. This is the formation of iron tetrachloride complex. To another portion of the iron hydroxide slurry, extra hydroxide is added. Iron hydroxide is unique in that it can be driven further in the reaction to form a separate product. The solid product of iron 3 hydroxide can continue to react with extra hydroxide. By doing so, it can form the iron tetrahydroxide complex. This complex is soluble and will begin to dissolve the iron hydroxide itself as the concentration of hydroxide continually increases. It's pushing the reaction even farther towards the products into a separate reaction. So there are a number of things that can occur in chemical reactions. There are lots of different ways that things can interact with each other. And Le Chatelier's principle really focuses on using observations and logic to decipher what is actually going on in some of these reactions. The fifth reaction also involves the use of iron 3 nitrate, but it reacts with potassium thiocyanate. The final complex of iron thiocyanate forms an intensely dark red solution. In fact, the solution is so intensely colored that it needs to be diluted so that way you can see anything that's going on. The reaction itself has also been used as fake blood in movies or theatrics due to the very low concentrations needed to produce an intense red color. Once it's diluted, you can see that by adding either additional iron or additional thiocyanate, both of them reactants, it will drive the reaction towards the product and create an even darker solution. The next reaction of the iron thiocyanate is to add sodium hydroxide. The sodium hydroxide preferentially can react with the iron. Again, iron will react with hydroxide to form either the brown iron 3 hydroxide solid, or if the hydroxide concentration is high enough, that pale orange solution of the iron tetrahydroxide complex. And this is what you can see happens here. After the thiocyanate, when the iron thiocyanate is mixed with sodium hydroxide, that deep, intense red color disappears and it forms the pale orange brown mixture that's unique for iron hydroxide. The iron preferentially prefers to react with the hydroxide. The last reaction looks at the formation of silver chloride. Silver chloride is a very insoluble salt, and this is the reaction of aqueous silver nitrate and hydrochloric acid, producing this bright white silver chloride salt. Silver chloride is a transition metal, and transition metals really have a tendency to combine with ammonia. When ammonia is added, it prefers to be bound, the silver prefers to be bound to the ammonia. It's removing some of the silver ion from the equilibrium reaction, binding it with ammonia, changing the equilibrium and shifting it from the solid product back into the aqueous reactant. You're removing silver ions from this equilibrium reaction to have them form the silver diamine complex, which is also clear and colorless. It looks like it changed back into the same thing that you started as, but it is a separate compound. That separate compound, that silver diamine, can continue to react, only this time by adding acid. Ammonia is a base, and by adding nitric acid, that H+ will react with the NH3 in this equilibrium, and it will form NH4+, the ammonium ion. When this happens, this reaction, the reaction of ammonia and H+, is removing ammonia from this intermediate reaction. By removing this ammonia as a reactant, the silver diamine complex can shift from product back into reactant. So in this step, it's increasing the amount of silver ion and increasing the amount of ammonia ion by decreasing the amount of the silver diamine complex. All of this occurs in the same test tube, in the same reaction vessel. So the chloride that was initially there is still there. Now, however, the silver is no longer hooked on to the ammonia. It's free floating back in solution. So now you added silver back into this initial step where it can form the solid silver chloride again. In a number of these other reactions, you were looking at how a reaction that's once removed from the initial reaction affects it. This last step is looking at how a reaction that's twice removed can affect the reaction. Equilibrium plays an extremely important role in chemistry because there can be many things that happen all at the same time in the same container. And being able to balance and being able to know where exactly the molecules and the ions are and how they're moving around plays a key role in any sort of chemistry that's done either in the lab or at high production levels. Overall, with Le Chatelier's principle, you should be able to see that a reaction can oscillate from one side to the other, generating either more product or more reactant, depending on the amounts of product and reactant that are either added or subtracted. Going through either in this example from the golden color to a dark blue color, and then back to the golden color, just by adding and subtracting reactants in the initial reaction.